Hello, everyone. Thank you so much for listening to this presentation. My name is Camila Apablaza, and I will be presenting the work called Do Shared Micromobility Options Reduce Traffic Congestion? Evidence from a Natural Experiment. This work is co-authored with Savannah Horner, Kay Lawson, and Dr. Omar Asensio. We all know and have been aware that shared micromobility devices like e-bikes and e-scooters have been offering cheap and convenient first and last mile solutions all over the United States and all over the world. For example, only in 2019, people in the United States took over 130 million trips, which represented an increase of more than 60% with respect to the previous year. However, evidence about how these type of devices affect traffic congestion and therefore contribute to reducing emissions is not clear. On one side, scooters providers have claims in which they mention that scooters and e-bikes actually help to decrease car trips with some evidence from French cities. On the other side, there are studies from cities like New York or Atlanta that claim that scooters actually do not displace cars, but displace modes of transportation such as public transit or walking, which would not lead to a decrease in car trips. This discussion is relevant because as transportation is the main source of greenhouse gases emissions, micromobility alternative could support efforts for climate change mitigation. So in this study, we take advantage of a micromobility ban that was implemented in the city of Atlanta on August 9 of 2019 because of the increase in accidents due to micromobility devices observed in the city, specifically at night. That's why in the red area showed in the map, which are the limits of the city of Atlanta, shared scooters and e-bike were not allowed between 9 p.m. and 4 a.m. Also, we know that there is an increasing number or amount of mobile platform data that is revolutionizing digital infrastructure and also incentives for electric mobility. And micromobility is one type of this type of mobility. So in this study in particular, we take advantage of the Uber movement data set that has recently been released that includes travel time between the entire Atlanta metropolitan area that has 831 census tracts. And particularly, we look at the city of Atlanta that has 133 census tracts. So we rely on the micromobility ban implemented in the city and on this newly released data set to answer the following research question. What is the effect of the use of micromobility transportation alternatives in urban traffic? To study this question, we implement a quasi-experimental design study to study the effect of micromobility in travel times or traffic congestion in 3 different experiments. These experiments are divided into groups. The first one is called recurring mobility because it deals with daily travel patterns or daily commute in the city of Atlanta. In this category, we have the Midtown Experiment and the Marta Experiment, which I'm going to explain later. The second type of experiments are the event-based mobility experiments, and in this case, we study particularly the Mercedes-Benz Stadium, which is located in downtown Atlanta. And we call it an event-based experiment because we look at sporting events occurring in this stadium. So it's a much more concentrated experiment with respect to the recurring mobility. So the methodology we propose improves previous approaches that included mostly self-reported data, including surveys and interviews. The first experiment is the Midtown Experiment, in which we use a triple differences estimator. To implement this triple differences estimator, we need 2 features to be able to create our treatment and control groups. The first feature is the availability of scooters in a given area or census tract. And the second feature is the implementation of the policy zone, or the implementation of the policy, which we can see in gray in the map. So with these two features and combining them, we have four groups or four neighborhoods that we use within the city. The first one is the treatment group that is shown in blue, which corresponds to Midtown. That is an area that is located within the policy zone and also that has scooters available, given the service areas provided by the scooter companies. Secondly, we have the bucket area in purple, which is also a neighborhood located inside the city of Atlanta limits, however, does not have scooters available for use. Third, the Cumberland area in orange is located outside the city limits and also has scooters available. And finally, the green area, which is called Sandy Springs, is characterized for being outside of the policy zone or the city of Atlanta limits, and also does not have scooters available for use. The second experiment is the Marta experiment, in which we use a difference in differences estimator to calculate the effect of the micromobility ban in traffic congestion. So for estimating this effect, we use a treatment group and a counterfactual or control group. The treatment group is shown in blue in the map and corresponds to those census tracts that have MARTA stations and that are located inside the policy zone, that is also shown in gray. The counterfactual group contains those census tracts that also have MARTA stations, but are located outside the policy zone. Finally, the third setup is the Mercedes-Benz experiment, in which we use a fixed effect model to calculate the difference pre and post policy of travel times. And we use the travel times between the pink census tract shown in the map, which is the census tract that contains the Mercedes-Benz Stadium, and all the yellow tracks, which correspond to those tracks that have scooters, and therefore people could actually commute from those yellow census tract to the Mercedes-Benz Stadium using a scooter. So those are the times that we use. The results of the study are summarized in the table. First, for the Midtown experiment, we find, using the triple differences estimator, that there is a congestion effect of 0.12 minutes per mile, which means that someone that is commuting in the city of Atlanta after the implementation of the policy will take an extra 0.212 minutes for each mile that they have to drive. Since this number is not so easy to understand, we translated this into an increase in travel times per trip using a typical commute in the city of Atlanta. And we found that the extra time that someone has to spend in traffic due to this ban ranges from 1.85 to 3.83 minutes per an entire trip. Secondly, for the Marta experiment, we used a difference in differences estimator, and we got an estimator of 0.29 minutes per mile, which means also that someone in traffic would spend extra 0.29 minutes per mile after the policy ban with respect to before. And this can also be translated into a range per the whole trip, ranging from 2.48 to 5.29 minutes for an entire trip. Finally, our event-based mobility estimations are larger in magnitude because, as I mentioned before, this is a much concentrated estimator, and that is calculated around a higher density of people, which is a sporting event. So in this case, the Mercedes-Benz estimator is 0.886 that can be also translated into a range per trip ranging from 7.43 to 16.32 minutes for an entire trip. This means that someone that is attending a sporting event at the Mercedes-Benz Stadium would take an extra 7 to 16 minutes to go back home after the implementation of the policy because scooters are not around anymore. To understand better these numbers, we used the value of time estimation that was calculated in another study of $26 per hour for the city of Atlanta. So this means that someone that is sitting in traffic for an entire hour in the city is actually losing $26. And using this estimation and our traffic congestion impacts, we find that the city could have a negative impact due to the implementation of the ban that ranges from $3.7 to $10.6 million per year. To have an idea about how large this number is, we found that this is equivalent to 8 years of the city's micromobility operating revenues, which means that it's 8 times the amount of money that the city receives for the fees that the micromobility and e-bikes companies pay for operating in the area. So a small summary of our results is that we find an increase in travel times ranging from 1.85 to 5.29 minutes per trip in a typical Atlanta commute. And this is using the estimate for the recurring mobility experiments. So this means that commuters significantly revert back to cars when they see that scooters are not available anymore. So contrary to what other studies found, in the city, we did not find that the majority of people were replacing scooters with public transportation or walking, but we found that a significant amount of people would actually replace the scooters with their cars. This is a very important opportunity to get sustainability benefits, and in particular, emissions reduction in the urban setting, because people are increasing the number of micromobility trips per year. And also studies show that they're shifting towards longer scooter trips. So they're using scooters to go further every time. Some of the policy recommendations of this study is that platform owners, such as the Uber platform or micromobility devices platforms, have very few incentives to share the data they own, and this causes poor data interoperability, which means that private and public institutions are not able to use this data to make more informed decisions. So we suggest 3 things. First is that there has to be policies for data disclosure, of course, of anonymized and aggregated records that are useful for public, private, and academic institutions to do research and to make better decisions. Second is ensuring the continuity and consistency of the data that is being disclosed, especially if some of these firms are going out of business. And third, data standards are not only important at the city level, but also at a regional scale, which can mean in this case, the Atlanta metropolitan area, because then public and private institutions across the entire area will be able to coordinate and make better decisions to improve people's quality of life. Thank you so much for listening, and I'll be glad to take your questions during the session.